Hello students. Today we are going to discuss homogeneous functions and Euler's theorem. Let us first define what is a homogeneous function. A function is said to be a homogeneous function if sum of powers of variables in each term is same. The sum of powers is called degree of the homogeneous function. Suppose we have 2x square y plus xy square minus y cube. This is the function given to us, function of f of x y. So this is one term, this is the second term, and this is the third term. What does the definition say? If sum of powers of variables in each term is same. So the variable over here is x and y. Sum of powers over here is 3. Over here it is also 2 plus 1, 3. And over here it is also 3. So this is a homogeneous function. Right? This can be simplified in a way, and this can also be written as lambda x into lambda y is equal to lambda to the power n into the original function, where it is raised to the power n, and n is known as the degree of the function. Right? We move with this question. Suppose the question given to us is 2x square y plus xy square minus y cube. We have to find out whether this function is homogeneous or not. We saw here that each term has a degree of 3. So this function is homogeneous. Right? But in case of complicated questions where we cannot just see the function and look at the terms and find out what is the degree, in that case we follow the following steps. We have to multiply each term by lambda. This is x square, lambda x raised to the power 2 lambda y plus lambda x. This will be lambda y square minus lambda y cube. Right? We open the brackets, 2 lambda square x square lambda y plus lambda x lambda square y square, this one, and this is x cube lambda cube y cube. Over here it will be this 2 lambda cube square y plus this lambda cube x y square minus lambda cube y cube. Okay, now lambda cube is over here, lambda cube is over here, lambda cube is over here. We take out the common and write 2x square y plus xy square minus y cube. This is right, x cube 2x square y plus xy square minus y cube. This is what we have got. This is function of x and y, what we discussed over here. This one. Okay. Now in case of complicated questions, how do we find out the degree of the function? Suppose we have this question. If z is equal to f of xy is equal to x cube plus y cube by x minus y, and what you have to show that z is homogeneous function of degree 2. You don't have to find a degree. It is said that it is of degree 2. You have to prove that this function is of degree 2. How will we proceed? The solution is, this is the original function. We multiply the variable x by lambda, y by lambda is equal to, this is x cube, lambda x whole cube plus lambda y whole cube minus by, lambda x minus lambda y. Then we open the brackets. This is lambda cube into x cube plus lambda cube plus into y cube by lambda x minus lambda y. We take out the common from here. Over here, if we take out the common from here, lambda cube x cube plus y cube. Again we take out the common from here. This will be lambda into x minus y. We got the original function, and then we cut this one cross, we get lambda square. That is equal to lambda square x cube plus y cube by x minus y. Right? So hence, what is the degree of the function? This is 2. So z is equal to f of xy is a homogeneous function of degree 2. We move to the next question, that is, show that the following function is homogeneous. What is the function? F of xy is equal to a x to the power minus beta plus b y to the power minus beta whole to the power 1 by beta. Right? Now we have to multiply each variable by lambda. F of lambda x comma lambda y is equal to, we multiply this by lambda and then whole raised to the power minus beta plus b. A and b are coefficients. These are not variables over here. Then lambda y whole to the power minus beta, then whole to the power 1 by beta. Right? Now what is the purpose? We open the brackets of this and then this. Right? A lambda raised to the power minus beta, x raised to the power minus beta, b lambda raised to the power minus beta, y raised to the power minus beta, whole raised to the power minus beta. What is common now? Over here, lambda raised to the power minus beta is also here in this term and also here in this term. We take out this as common. Lambda raised to the power minus beta, a x to the power minus beta, the remaining b, this b, and the y raised to the power minus beta whole raised to the power minus 1 by beta. Right? Now how should we proceed now? Over here, lambda minus beta into, we multiply the power into 1 by beta. Then the bracket a x to the power minus beta plus b into y to the power minus beta raised to the power 1 by beta. Right? Then this will be cancelled over here. Minus minus plus lambda, then a x to the power minus beta plus b y to the power minus beta whole raised to the power 1 by beta. You see, lambda into this is what is the original function over here. Right? So this becomes is equal to lambda f of x y. So this is a homogeneous function of degree 1 because what is raised to lambda is 1. Right? We move to the next topic, that is Euler's theorem. Euler's theorem. What does this theorem say? If z is a function of x and y, and this is a homogeneous function of degree n, then x into delta z by delta x plus y into delta z by delta y is equal to n into x z. This is the first derivative with respect to x. This is the second derivative with respect to y. This is the degree of the function, and this z is function of x and y. This is what the Euler's function says. Now we move to the verification of the Euler's function. Right? Suppose we have the question z is equal to x square plus y square by x into y. We have to verify the Euler's function. It means we have to do this operation, right? So we have to find delta z by delta x. We also have to find delta z by delta y, and also we have to find the degree of the function, right? Let us find delta z by delta x. We can simplify this x square by xy plus y square by xy. This is x by y, and this is y by x. Now we differentiate this. Okay. When we differentiate with respect to x, y will be constant. So this will be 1 by y, and this will be y by x square. We got delta z by delta x. Now we have to find delta z by delta y. Over here, x will be assumed to be constant, right? We differentiate this. So this will be minus x by y square plus this will be 1 by x. We got two things for the verification of the Euler's function, that is delta z by delta x and delta y by delta y, delta z by delta y. Right now we find out the degree of the function. How do we find out the degree of the function? That we have already done. You know the function is z is equal to x square plus y square by xy. You know it's a function of x and y. So you multiply this by lambda, y also by lambda, and then lambda x square plus lambda y square by lambda x into lambda y. You open the brackets, lambda square x square plus lambda square y square by this is lambda square y. This will be, take out the common, lambda square x square plus y square lambda square, right? Then y into x. You cancel this and you are left with just the function but no degree, right? So the degree is 0, right? Now we have to prove that x into delta z by delta x plus y into delta z by delta y is equal to n into x. That is verification of the Euler's theorem. So whatever result we have got, we write it over here. This is 1 by y minus y by x squared plus y into minus x by y square plus 1 by x. So this will be x by y minus, you cross this, you will be left with y by x minus, you cross this, you will be left with x by y plus y by x. Y by x plus y by x minus 1, cancel it. So this comes out to be 0. Hence, you have verified the Euler's theorem, right?